All right, good morning. So at the end of the last class, we had finished implementing an array-based stack. Right, so remember, stacks, they only have two fundamental operations. There's pop and push. Right? If you analyze the pop implementation here, right, you'll notice that there's no loop, basically, here, right? Essentially, there's an if statement. Right? There's an array access, right? One assignment, another assignment here, and then a return statement. Right? And so pop, you can conclude, runs in O1 time, right? Constant number of operations. When you look at push, right? So if you push into an array, if you push into a stack, and the array in the stack has capacity to hold the element, right? Then you only have to, so there's a if statement, right? So one comparison, one assignment, or a one update to the index, and then one update, one array access and assignment, right? So also constant time. However, if you run out of capacity in the array, right, this is where you've got this loop, and that loop runs, the number of times that loop runs is proportional to the number of elements in the stack. And inside the loop, the operation that happens in the body, that runs in constant time. So that's an ON operation right there. Right? And so you can see that the worst case complexity for the push operation is in ON. Right? If you're in a situation where you really cannot, or you think that you really cannot afford to pay that ON price, you have to look at a different stack implementation. Now, whether or not you're truly in such a situation is a completely separate story. Right? But the question that I want to address today is can you avoid this ON price, ON worst case complexity, in a different, using a different stack implementation? Right? So that's the next set of lecture slides. So that's stacks 2. Where are we? Reverse. Stacks 2. All right, so the first thing we're going to do is we're going to create a stack interface. So we're going to have, so that we can have multiple different stack implementations. You'll use all the implementations the same way, right? Because they're all going to implement a common interface. So our interface for a stack is pretty straightforward. Right? So our interface is just going to be called plain old stack. Right? It's an interface, not a class. Right? Now you just list the methods that you want to include in the interface. Right? So I'd like every stack to be able to tell me what its size is. So I'm going to put in a method called size. Right? Similarly, we can put in, it's often useful when you're writing code that operates on stacks. You want to know, is the stack empty or not? Right? You could just use size and check if the size is greater than 0. If the size is 0, which would indicate an empty stack. Right? But it's nice if you put in a method that called isEmpty that returns true if the stack is empty. So I'm going to come back to this one because we haven't seen this type of method before yet. So I'll return to this in just a moment. Right? What other methods does our stack class have? Well, it can have a push method, and it's going to have a pop method. Right? This is for a stack of strings now, not for so this is an interface for a stack of strings. Right? Later on, probably in 2 or 3 lectures, we're going to be able to create a stack that can hold any type of element. So we're going to make a generic stack. For now, we're talking about stacks of strings. All right, so back to this default method here. So in an interface, you are allowed to have what's called a default method. So a default method is marked as being default. Right? A default method has an implementation. Right? So in this case, there is a body for the method. Right? So this is different. Right? So all of the previous interfaces we've seen, right? They have method declarations, but they don't have any method bodies. Right? So there's no implementation. For a default method, the default method does have an implementation. You're restricted on what you can put inside the method body here. So remember, this is an interface, right? So there are no fields, right? So you don't know, so this method needs to work for every possible kind of stack. You have no access to the fields of any one of the stacks. You don't even know what the fields are because you don't know if someone else makes a stack class that implements stack, you have no idea what their implementation is going to be. So this method right here cannot access any fields belonging to a stack. Right? At least it can't access them directly by name. The only thing that it can do is use other methods in the interface, right? So for example, isEmpty is allowed to use the size method, right? It can use the size method because the interface says every class that implements this interface must have a size method. So we can legally call size here, right, and check if the size is equal to 0. You're also allowed to use methods that belong to java.lang.object, right? So you can use methods like isString or equals, hashcode, and whatever other methods are in object. The reason you can do that is because any class that implements stack, right, is also a big O object. So you're allowed to use those methods as well, right? So default method has an implementation. It can use methods that are in the interface, and it can use methods that are in object. And that's what this slide describes right here. Okay, so these things appeared in version 8 of the language. So prior to version 8, there were no default methods allowed. The reason they were introduced into the language is because once you make an interface and it becomes widely used, you cannot easily change that interface anymore. Because once an interface becomes widely used, lots and lots of people have created code that rely on that interface. If you then change that interface, everybody that's used that interface now has to go in and change their code, which is impractical for a language like Java where it has many, 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 many users. Right? So if you can't add methods, so if you can't change an interface once you've released it to the public, and you realize that you want to do something where you need to add methods to the interface, right? The language designers had to put in a mechanism to do so, and that was the default methods, right? And so Java 8 also added another major feature to the language called lambda expressions. Right? We don't talk about those in this course, but they are a significant addition to the language. By adding these things, they had to adjust many of the interfaces in the standard library. The only way that they could adjust the interface without breaking everybody else's code was to add in these default methods. Right? And so you can see here that languages evolve over time. Right? Java being I guess it's a mature language now. It's changed many times, right? And so it has to, so when it adds new features, that adds some additional complexity to the language. All right, so we have an array list-based stack, and we have an array-based stack. We can change both of them easily to implement the interface, right? So our list-based stack, we can change it to implement the interface just by saying it implements the stack interface. And that's it, you're done. You don't have to do anything else, right? So if you have a class, so if you decide that you want an interface because you want to have multiple different implementations of that interface, right? It's relatively easy to take an existing class and change it so that it now implements the interface, right? All you have to do is insert the implements followed by the name of the interface, right? Nothing else changes. So that's nice. Oh, okay. Now, to address that ON complexity of push, we're going to completely change the implementation of the stack. So instead of using an array, we're going to use something called a node. Right? So once again, right, for our array list-based stack, so both the array list-based stack and the array-based stack, push has worst case ON, right? Because you have to, occasionally you have to adjust the size of the array. So one way to do this is to implement what's called a sequence of nodes. And so many data structures will represent elements of a collection using nodes, right? So if you've taken, I think most of you have taken Sys 204. So there you should have learned about trees, right? In trees, you would have been told that they're a collection of nodes or vertices, right, joined by edges or links, right? And so trees are an example of a data structure that's typically implemented using nodes. Linked lists, so we'll look at these later in the course, probably in a lecture or two, right? Another example of a data structure that's implemented in nodes. Graphs, you also should have seen in 204. There's actually an entire course, Math 401 is an entire course on graph theory. So if you want to make a collection based on nodes, what you need to know is that a node stores an element. right? Or a reference to an element in the case of Java, right? A node then also holds a reference to 0 or more other nodes, right? And so these references are often called links, right? So a node links to another node, or possibly multiple nodes. Now for a stack, we have what's called a linear collection, right? So it's one element followed by another element, followed by another element, and so on and so on and so on, right? Trees and graphs are nonlinear data structures. So in a stack, we have a sequence starting at the top element, right? Every element is connected to the next element deeper in the stack. So for a node for a stack then would store either an element or a reference to an element, right? And then it stores a reference to the next node in the stack. So for example, here's a stack containing one string, right? So we're going to keep track of which node is the top node of the stack, right? Inside of a node, so that thing right there is a node, right? So inside of a node, there's an element, or a more correctly, there's a reference to an element, right? And then there's also a reference to the next node in the sequence, right? So there's our element, there's our link. Right? So the arrow is indicating our reference to the next element in the sequence, or the next node in the sequence. So if we want to push an element onto the top of this stack, right? Remember, our nodes are holding the elements of the stack, so we're going to make a new node. Right? So a new node appears, and you store the element or a reference to the element in the node. Right? So we're going to push a B onto the stack, so we store the B in the newly created node. Right? I now need to join this node to the existing stack. Right? So this node has a link, so I want to set its link so that it points at the current top node. Right? So in other words, I want to do that. Right? All right, so now I've got a stack. It's got two elements in it, but the top is incorrect, right? The top is now the B. So I need to adjust that top reference so that it now refers to the B, or to the node containing the B, right? And now we're going to keep track of the size of the stack as well. So we want to add 1 to the size of the stack because we just added a new element to the stack. Right? So if you push another element onto the stack, so we push a C, right? Again, you're going to make a node. You're going to store the element in the node. You're going to link that node to the old top of the stack, and then you're going to adjust the top element. You're going to adjust the reference to the top. You're going to adjust which node is the current top node. Now, if you want to remove an element from the stack, right, we need to pop that node off the stack. Right? So we're going to remember what is in the node. So I'm going to remember what is the element that's in the node. Right? That's going to be the C in this case. Right? I want to adjust top so that it now points at the B, right? Because we're going to remove this node from the top of the stack. Right? Now we've got a reference. We've got a reference to the top node. Right? Inside the stack, there is no reference to the second node. There's no reference to the third node. Right? So we're not keeping explicit references to each node. Right? If we were, this would basically be an array-based stack, right, or a list-based stack. So what we're going to do is we somehow need to make top point at B. So what we're going to do is we're going to follow top, right? So that's the top node. We're going to follow its next link to get to the second node in the stack, right? So follow that link, right? And that gives us the second node in the stack, right? And so we can set we can set top to point to that element now, or to that node. Okay, so we can now unhook that node, the C, from the stack, right? So it goes away now. Subtract 1 from the stack size because we just removed an element, and return whatever value we remembered in step 1, right? So we're going to return this reference to the string C, right? And so when I go to implement push and pop, you just have to follow the slides, right? You're literally going to implement step 1, step 2, step 3, step 4. All right, so if you want to draw so we need to make a node class now to represent the nodes of the stack, right? So for a stack, a node is going to store an element or a reference to an element, right? And it's going to store a reference to the next node deeper in the stack, right? So our node class, right, is going to be an aggregation of one element, right? So it's going to be an aggregation of one string, right? So a node has a string, right? Now a node refers to another node, right? So it's going to store a reference to the next node deeper in the stack, right? So every node has a reference, right, to the next node deeper in the stack, right? So in other words, inside the node class, right, there's going to be a field called next, right, where next is referring to the next node in the stack, right? So every node is has an association with another node, right? So node, each node is an aggregation of one string, and it's an association with another node. Okay, so we're going to make a linked node-based stack. So I'm going to call that linked stack. Right? It's going to implement the stack interface. Right? There's only two fields in this class. Right? There's the size, so the number of elements in the stack, and there's a reference to the top node. Right? And that's it. Now, what else? There is another class inside of the stack, inside of the linked stack class. So we're going to put our node class inside of the linked stack class, right? I'll explain what this means in just a second, right? So every node, right, is an aggregation of one string, so there has to be a field that stores the string, right? It has an association with another node, so there has to be a field that has type node, right? So elem, that's the element. Next, that's our link to the next node. Right? This is just a class, so if we want to, we can put in a constructor. Right? So here I've got a node constructor that takes in a string and a reference to the next node. Right? All it does is set elem, this elem to elem, and this next to next. Right? There's no composition happening here, right? No composition here, no composition over here. So there's no copying of the element. There's no copying of the next node, right? You can simply write this elem equals elem and this next equals next, right? Okay, now what is this static business going on, right? So in the previous lecture, we saw an example of an inner class, right? So an inner class, nested inner class. So a nested class is a class that's defined inside of another class. So node is also a nested class, right? An inner class is a nested class that is not marked as being static, right? So our, what was it? It was our iterator. So it was our range iterator class was defined as a nested inner class, right? A static class is different. It's not an inner class, right? So it's called a static member class is the simplest kind of nested class in Java, right? So it's the simplest class that you can define inside of another class. If you have a static nested class, it's just an ordinary class that happens to be defined inside of another class. Right? That's all it is. So it's as if you had created a class and decided to plunk it inside of another class. You can use it as though it were its own class. Right? So remember, when you had an inner class, right, you typically cannot use the inner class as its own standalone class. Right? The inner class exists to serve the class that it's in. Right? Here we're in a slightly different situation. Right? So unlike other kinds of nested classes, right, a static member class, which is what we have now, cannot refer to the private members of the enclosing class. Right? So our node class does not have access to the private fields of linked stack. Right? The node class can only see its own fields, right? Or whatever. I guess if linked stack had public fields, it could see those too, right? Instances of a static member class can exist in isolation of the enclosing class, right? So remember, in the previous lecture, you can't make a range iterator without a range. It doesn't make sense, right? A range iterator iterates over a range, so there has to be a range to iterate over. In this particular example, it's possible to make a node without having a stack. Right? So here you are allowed to make a node object, right? And it can exist without belonging to a linked stack object, right? So node is literally just a class that happens to be defined inside of another class. right? And that's all it is, right? So because it's just a regular class, oh, sorry. Because it's just a regular class, right, you can put things in like constructors and methods if you wanted to, right? We don't need methods in this case, although you could put them in, right? We don't even really need this constructor. You could just access elem and next directly, right? But here it's convenient to have a constructor. Yeah, question?
So is there truly no difference in a nested not in a class than the top level class?
The only difference is the way that you would access it from outside of the class that it's in. Right, so if you wanted to make a node outside of linked stack, this would have to be public, so it'd have to be accessible, right? It's marked private, so you can't access it. If this was marked public, then you could access it. The name of the class then becomes linkedstack.node, right? So that its name becomes a little bit different, right? But that's it. But otherwise, it's literally the same as a class defined inside of another class. Okay, so what about the linked stack itself? Right, so no argument constructor for linked stack. So let's just go back and look at our, here we go, our fields. Right, there's a size and there's a top node. Right, so the no argument constructor makes an empty stack. Right, so in an empty stack, the size is 0. Right, there is no top node, so we set this top to null. Right, if you wanted to, you could put in other constructors here. Right, so you put in a constructor that takes in a string. Right, it pushes the string on top of the, so it makes a stack with one element that has the string. You can put in a copy constructor, you can put in whatever constructors you want. Right. Our size method, so remember our interface for stack says there must be a size method. Right, but that's easy because our stack keeps track of its own size, so we can just return this dot size. Okay, so what about push? So remember how push works, right? So to push an element onto the stack, make a new node, set the element in the node, right? Adjust the node's next link so that it points at the old top node, right? Now adjust top so that it points at the new node, like that, right? And then increase the size of the stack by 1, right? So just follow each one of the 4 steps, right? Make a new node, so a new node. Set the element in the node to elem, so I can use the constructor to do that. Right? Link that node to the current top node. Well, I can use the constructor to do that too. Right? So that's all one line because I have a constructor that does all the work for us. Right? So our node constructor sets the element of the node to that. It sets the link for the node to that. Right? So I've got 1 and 2 all done in one line of code. Set top to refer to the new node. Well, that's easy, right? I made my node n, so this top is now n. Right? Step 4, add 1 to the stack size. That's easy too. This size plus plus. Right? And there's push in 3 lines of code. Any questions about this method here? Okay. So to pop an element off the stack, you need to somehow, so when you pop an element off the stack, you need to return the element, right? I'm not returning a node. So we need to remember what is that element that's sitting inside of that node. Right? So we need to obtain a reference to the element stored in the current top node. Right? I now need to set top so that it points at the second node in the sequence. Right? And to get to the second node in the sequence, I'm going to follow the current top node's next link. Right? And that will take me to the second node in the sequence. Right? Now, conceptually, what happens is this node disappears, but you don't have to, there's no way in Java for the programmer to remove an object. Right? So as soon as you no longer have a reference to the top node, right, the Java virtual machine can eliminate this node from memory. Right? But you're not going to do it yourself. Right? So conceptually, the top node disappears. Right, but the programmer doesn't have to do anything to explicitly remove the node. Right, and then you're going to subtract 1 from the stack size. Right. Oh, step 4: return the reference to the the string C that we had in the first step. Okay, so ignore the if statement for now. Right, I want to remember what is sitting in the current top node. Right, so the string that's sitting in the current top node is just this.top.elem. right? So I'm going to return that as the last step, right? Adjust top so that it points to the second node in the sequence, right? So the current top node is this dot top, right? Now remember that node holds a reference to the next node in the sequence, and it's called next, right? So this dot top dot next is the second node in the sequence. So simply assign this dot top to refer to the second node in the sequence, right? Decrease the size of the stack by 1, return the popped element, and that's it, right? The only strange part here is that line right there, right? That looks a little bit weird, right? We're going to adjust the, we're going to make our field top refer to a new node by actually following one of the fields inside of top, right? So what you have to remember here is that next is actually a reference to the next node in the sequence, right? And so this top next, that's always the second node in the sequence, right? Which you can assign to this dot top, right? Okay, any questions? Oh, sorry, the if statement. You can't pop an empty stack. So if you try to do that, we're going to throw an exception, right? And so we're going to test, is the stack empty, right? Remember, we have an isEmpty method in the interface, so that means we've got it in our stack, right? If the stack is empty, throw an exception of some kind. Here, I've elected to throw a runtime exception. You could throw a different type of exception if you wanted to. All right, any questions here? All right, this all works in Java because everything is Java and Python, because everything's references, right? These nodes, right? So this dot top and this dot top dot next, these are all references, right? And so that's why all of this works. Okay, iterating over a linked sequence. So if you wanted to print a stack, what you have to do is you have to, if you wanted to print a stack, the string that you would generate probably includes the elements that are in the stack, right? So you might generate a string that says top, then the top element followed by the second element, followed by the third element, followed by the bottom element, right? You might generate a string that looks like that. To generate that string, you have to iterate over the sequence of nodes, right? To do anything with the stack, right? So if I need to get anywhere, if I want to do something with an element in the middle of the stack, right? I somehow have to get to that element in the middle of the stack, and that involves iterating over the sequence of nodes, right? Because all that the linked stack class has is a reference to the top element, right? So to do anything with an element that's not at the top involves starting at the top and moving to the node that you want to do that you want to perform the operation on, right? And so this thing here, iterating over a sequence of linked nodes, this is a very common operation when you're working with any linked structure, right? Okay, so you can iterate over the sequence of nodes, right? Because you know where to start. That's just this dot top. You know when to stop, right? Because the bottom node, its next link is null, right? And so you can just iterate over the nodes until you find a null next link, right? Starting at the first node of the sequence, right? You just follow each link to the next node, right? Until you reach a null node, right? So this is the general pattern for iterating over a sequence of linked nodes, right? So you're going to make a variable n or something else, right? You're going to choose your starting node, right? For a stack, we're always going to start at the top, right? For some other data structure, you might not start at the top, right? You might have a reference to some internal node, right? As long as n is not null, you can do something with the node, right? So if n's not null, you can look at the element, right? You can look at the next link, right? You can do something with n, right? Without worrying about a null pointer exception, right? Once you're done with n, you want to go to the next node, right? And so you can just set n to be equal to n dot next, right? N dot next, that's the node after n, right? So I can assign that to n, and that advances n so that it points at the next node in the sequence. You have to remember, right, after the loop, you can't use n, right? So you can't use n to do something with the node, right? So I can't look at the element in the node. I can't look at the next link of n anymore, right? Because when you hit this point here, right, that condition is not true, which means n is null at this point, right? You can reuse n, you can assign it to a new node, right? But you can't use n to access the element or next link here, right? So remember, don't use n here. Oh, sorry. Okay, so if we start at the top sequence of the, if we start at the top node of the stack, right? So n points at the top, right? We can do something with this element here, right? So for toString, right, we would write C into the string, right? Now I'm done with this node, so I can advance n to the next node, right? How do I get to the next node? I just follow n's next link, and that takes me to the b, right? So in toString, I would print the b to the string, right? And then follow n's next link to get to the a, right? Print the a to the string, follow n's next link, right? And that gets me to null, so the loop stops. Right? So as soon as n is equal to null, the loop ends, right? N's now null, so don't use n for anything. Right? So for toString, we could implement it like this. Right? I'm going to use a class called String Builder, which I haven't talked about in the course. You could just use string. The more efficient way is to use this thing called String Builder. String Builder is the, remember in Java, strings are immutable, right? So once you make a string, you can't change it. Right? String Builder is the mutable version of string, right? So it's a type of string where you can change the contents of the string. Right? So I'm going to make a new String Builder object that starts with the string stack and a colon. Right? I'm now going to use our general iteration pattern. Right? I'm going to make a variable n. Right? I'm going to set it to the top node of the stack. Right? If n's not null, right, I know that there's a node sitting there. Right? So for this particular version of toString, I'm going to add a new line character to the end of the current string. Right? So \n, that's new line. Right? The append method for String Builder appends that string, or that character in this case, to the end of the current string. Right? So our string, so b is now stack colon new line. Right? Then I'm going to append the string representation of the element. Right? So I can append n.elem. That's the element sitting in the node. Right? If you call append with an object, which this is, right, that's an object reference. Right? Append will automatically call toString on that thing there and join the string representation of the element to the end of the current string. So it's going to be stack colon new line string representation of the element. Right? Now I'm done processing the element. Go to the next node. Right? After I've processed all the nodes, I can return the string. Right? So the way you return a string from a String Builder is you call the toString method on the String Builder object. Right? But all that's happening here is we're just using our general iteration pattern, right, to iterate over the sequence of nodes. Any questions here, right? Or any questions about iterating over a sequence of nodes, right? You have to do something like this over and over and over again whenever you are, whenever you're writing algorithms on a linked sequence, right? On things like trees and graphs, it's much more complicated, right? Because there's multiple paths through the data structure. For the linear data structures, it's relatively straightforward. It's just a simple while loop. Okay, so this is the first time we've seen a class that has a reference to itself, right? So the node class is an example of what's called structural recursion, right? So the structure of the node class is recursive, right? Every node has a reference to a node. That node has a reference to another node. That node has a reference to another node, and so on and so on and so on, right? Like every other recursive thing, like algorithm or structure, the recursion has to end at some point, right? And so the way that recursion ends for our node class is that eventually you get to a next link that is null, right? Indicating there are no more nodes in the sequence, right? Because of this structural recursion, anytime you look at a node, whether or not it's the top node, right? You can imagine that that node is just the top of another stack. So in this stack here, right, that node is the top of the stack, right? But if you look at this node here, right, you can imagine that's the top of the stack that consists of the B and the A, right? And if you look at the node here, you can imagine that this is the top of a node, top of a stack that consists of just the element A, right? So whenever you get a node, you can just imagine that's the top of some kind of stack, right? Once you get this clear in your head, right, it becomes very easy to write recursive methods on these types of data structures, right? So remember, a node is just, any node is just the top of a stack, right? So we can rewrite toString so that it becomes recursive. Okay, so here's my toString method. The toString method is going to call a recursive helper method, right? So inside toString, we're going to start with the string stack colon, right? We're going to get a reference to the current top node, and now I'm going to call my helper method. It's the helper method that's recursive, right? So I'm going to call the helper method passing in the top of the current stack, right? Now, when you look at toHelper, right, what you have to remember is that n is the top of some stack, right? In our example, it could be the top of, it could be the C, it could be the B, or it could be the A, right? It's just the top of some stack, right? Okay, so every recursive method has a base case, right? So our helper method knows to do nothing if the node that's passed in is null, right? So toString helper is going to generate the string representation of a stack starting at n, right? Starting at that top node, right? So if you pass in an empty stack, right, the string representation of the empty stack is just the empty string. So you can return there, right? If the stack is not empty, right, then the string representation of a non-empty stack is the new line character followed by the element followed by the rest of the stack, right? Followed by the string representation of the rest of the stack, right? So that's what that recursive call is doing, right? To generate the string representation of a stack, you generate the string representation of the top node, followed by the string representation of the rest of the stack, right? You can get the string representation of the rest of the stack by recursively calling the method, passing in the next node in the sequence, right? And then you return the string s, right? And so there's the recursive version of toString, right? And this is the general pattern that you would use to write any method that iterates over the sequence of nodes recursively, right? Your base case is typically, am I at the end of the stack, right? Am I at the end of the sequence, right? If I'm not at the end of the sequence, do something, right? And then do something with the rest of the stack, right? And so that's how that recursive method works there, right? I don't know how much they teach you in 204 with trees and graphs, but many of the tree and graph, the easiest way to think about many tree and graph algorithms is to think about them recursively. With a linear sequence, it doesn't matter if you think about them recursively or iteratively. They're both the same. All right, any questions there? Right, so that's your first introduction to a linked sequence. Right, you're going to see these over and over and over again as you progress through computing science. Right, so if you take SYS 220, the C course, you're going to see how you implement a linked sequence in C. SYS 220. Yes. If you take data structures, you're going to see linked sequence all over again, right? You're going to have to implement a linked list. You'll have to implement binary and non-binary trees. You might have to implement graphs and other data structures like that.
That's C language, right?
No, SYS 235 can be taught in Python, Java, or C, depending on the instructor.
How about 220, how about 221?
What's 221? Architecture is C. Yeah. Oh, okay. Now, at the end of the last class, sorry, at the beginning of the last class, I told you I'm going to skip over a part of a lecture. All right, so I'm going to go back and do that now. Oops, sorry. Okay, so this is the beginning of the previous deck of slides. So one of the uses of a stack is to convert a recursive method into a non-recursive method. Right? So for the example that I'm going to show you here, it's going to seem like a pointless example of doing this. Right? But it shows you or it illustrates the general idea behind how you can take a recursive method and convert it to an iterative one. Right? The reason you want to do this is because if you write a recursive method and you try to solve a large problem with a recursive method, on many computer architectures, you won't be able to solve the problem. You'll run into an issue that I'm going to show you here. Right? And so if you convert it to an iterative version of the problem, then you can solve the larger versions of the problem.
We're back to the beginning, right?
Of the previous lecture. Okay, so here's a little recursive method called power of 10. Right? So power of 10 computes 10 raised to the power n, where n is positive. Positive or 0. Right? So 10 to the 0 is 1. That's easy. Right? If n is bigger than 0, can you stop talking, please? If n is bigger than 0, then 10 to the power of n is just 10 times 10 to the n minus 1. Right? Pretty easy, right? Okay, so when you call this method in a language like Java or C, right? This is what happens this is an example of what happens in memory, right? So somewhere you've got a main method, right? You call power of 10 to 3, so this should return 1,000, right? So what happens is this method starts running in memory somewhere, right? So it starts running here in this particular case, right? Now technically what happens here is that this runs on what's called the call stack, right? So it's an area of memory called the call stack. That area of memory holds the memory that's used by, in Java methods, right? So what appears in memory are any of the local variables belonging to the method. Also any of the parameters belonging to the method, right? So we've got a parameter n, right? We've got a variable called result, right? So n, right? There has to be memory for n. There has to be memory for result. Right? When you call the method, right, the 3 gets passed to here and gets copied into n. Right? So there's the 3 there. Okay, so what does power of 10 do when the value is 3? Well, it recursively calls itself. Right? It calls itself with 10 times power of 10 to 2. When you call a method, it appears on the call stack. So a separate version of power of 10 appears. Right? I don't think they normally tell you this when you first learn recursion. And so one of the traps in learning recursion is that you think when I recursively call a method or a function, right, that method or function is running inside of itself. That's not what's happening. Right? The recursive version of the function or method runs separately. So there's a second version of power of 10 that appears. Right? It gets its own value of n. It gets its own result. Right? Notice you're sucking up memory every time you call a method or function. Right? Okay, so n is 2. What does power of 10 do when you call it with 2? Well, it calls itself with 1. Right? That's a method call, so another version of power of 10 appears. Right? It gets its own value of n and result. Right? So there's 1. Right? What does power of 10 do when you call it with 1? Well, it calls itself with 0. Another version of the method appears. You can see now, if you try to solve a large recursive problem, what ends up happening is you have many, many versions of the method trying to run in memory. On most computer architectures, the call stack is limited in size, right? So eventually you'll run out of memory on the call stack, and the method will stop running, right? That will almost certainly crash your program. Okay, so we've reached the base case here, right? N is 0 is the base case of our method, so result gets the value 1. This version of the method finishes running. It returns the 1 back to its caller, and this can disappear, right? So 1 returns back to the caller. That version of the method disappears, right? The result is 10. So this version is now done, right? It can pass, oops. it can pass its return value back to the caller, right? And now this one can disappear. Right? That version is now done, right? So it can pass its value back to the caller, and it can go away. Finally, the original invocation of power of 10 is done. It can return 1,000 back to the caller here, right? And it's done. Right. Okay, so if you want to take a recursive method and turn it into an iterative one, right, you can simulate that stack yourself, right? So the basic idea here is I want to push some information onto a stack, right, to remember what needs to be done when each recursive call returns, right? So in power of 10, what do you need to do when each recursive call returns? Right? So when each recursive call returns, right? So when that 100 returns, right? You need to multiply it by 10. Oh, sorry. Right? Multiply the return value of the recursive call by 10. Right? All right. So I'm going to simulate all this using my own stack. Right? So every recursive call that's not a base case, we're just going to push a 10 onto the top of the stack because I need to remember, hey, I need to multiply by 10. Right? Okay, every recursive call, something happens to n. Right? What happens to n? Well, n goes down by 1 each time. Right? So n decreases by 1 every time you recursively call the method. Right? So here are my recursive calls simulated using a stack. Right? So there's my stack. Right? As long as n is not 0, I'm going to push a 10 onto the stack. Right? The reason I'm pushing the 10 onto the stack is to remember I need to multiply the return value by 10. Right? N is the variable that controls how many times the loop runs, how many levels of recursion there are. Right? So every time I push a 10 onto the stack, I've done some work so I can decrease the level of recursion by 1. Right? What happens in the base case? Right? So a recursive call that reaches the base case results in a 1. Right? So I'm going to start computing the product using the value 1. Right? So my result is 1 because that corresponds to the base case. Right? Now, where are the recursive cases? They're sitting on this stack that I just created. Right? So there's n 10s sitting on this stack. Right? So pop the stack until it's empty. Every time I pop the stack, that's like returning from the recursive method. So I'm going to multiply the result by the value that's popped off the stack. Right? So while the stack is not empty, pop the stack, multiply it by the result, and put it back into the result. Right? When the stack is empty, you're done. You've got your result. Right? And so when you look at this thing, you say, well, that's a really stupid way to compute the power of 10. Right? You could just write a simple loop. Right? But the nice thing about this is that it actually generalizes. Right? So you can take this technique, right, and you can generalize it to solve any recursive, to convert any recursive problem into an iterative one. Right? It's often very complicated to do because you have to simulate what's happening in the call stack every time. Right? So it's not trivial to do in most cases, right? But it's the basis of the idea behind converting, it's the basis of one idea of converting a recursive method into a non-recursive one. Right? It uses a stack to simulate what's actually happening in hardware, on your computer when you run a recursive method. Okay, there is no other example right here. So, so that's all I want to talk about regarding converting a recursive method into an iterative one using a stack. Right? Probably in data structures, you'll see this technique again. All right, any questions about linked stacks or array-based stacks or anything else? Okay, so that's it for today. I'll see you again, I guess, Friday morning.